So, welcome everyone to our weekly TCS seminar after the winter break. Today we will have the pleasure of listening to Benny Sudakov from ETH Zurich. Benny is famous of his work in extremal probabilistic combinatorics. He is also a fellow of American Mathematical Society. And also he is the advisor of a lot of other famous mathematicians doing combinatorics. Today he will tell us about C4-free subgraphs of high degree with geometric applications.
Thank you very much. It's a great pleasure to be here. And it's a good audience to talk about the result I want to present, because there is one particular statement which I'm going to present. I will not show the proof, but proof can be found in the paper. I will show the application, and the feeling of me and my co-authors is that this result should have more applications. And actually this is why I'm going and giving this talk in various places, because I hope people will look and recognize that they can use this result for something. Okay, so let me first tell you who are my co-authors. So this is a joint work with Zach Hunter, Alexa Milosevic, and Istvan Tomon. So Zach and Alexa, amazing graduate students I have in ETH, and Istvan, he's now in Umeå in Sweden. So let me start with motivating the result. And one thing you observe when you do various extremal or geometric problem is that assuming that your graph is C4-free makes life much easier. And let me give you an example. So I start with a basic proposition, and I'll tell you to what it connected. So imagine G is C4-free graph with minimal degree, say, break it. The chalk, minimal degree, at least 2t. Then I claim G contains every 3t anti-vertices as induced subgraph. And so this is motivated by famous Garfash conjecture. So Garfash conjectured that if you have a graph which does not contain a fixed tree t as induced subgraph, then this graph is chi-bounded, which means its chromatic number is bounded by a function of clique number. And here we're showing that if you tell me in addition that your graph is C4-free, you get something stronger. You get degree bounded. Right? So if you tell me that you C4-free and you don't contain given 3t as induced subgraph, you have a small degree, right? You degenerate. Okay. So the proof is very easy. So let me do it. It's by induction on t. So imagine you have your favorite 3t, and I write it like I find in this 3t a leaf, u, v, and I delete from this tree this leaf, t minus u, and I use induction, right? So this is obviously tree of smaller size. So here's my graph G, and imagine I already embedded somehow this tree here. So this is t prime already embedded as induced subgraph, and here is this image of the vertex V, right? And this V has a big neighborhood in this. So this is my graph G, right? So this is my picture. And so what I want here to find an image for the vertex U, and there are a few things to worry about. So first of all, obviously I draw this neighborhood disjointly from the copy of T prime, but it shouldn't be. So some vertices can be here. And moreover, the vertex here, right, so call this vertex X, some other vertex, can have a neighbor here, right? And I can also not use, right, so if, let me just do a picture. So if this is an edge, then this vertex is forbidden, because if I call this vertex U, I get a copy of T prime, but it would not be induced. But observe that because I'm C4-free, right, by C4-free, any X which belongs to copy, let me write it like this, copy of T prime, has at most one neighbor in NB, right? Just because if it had two neighbors, you get four cycle, right? So, because this is a neighborhood in two vertices, right? So if you have two neighbors, right? So let's have V, so this is NV. If X has two neighbors, you get a four cycle, so this is four. And therefore, you easily see that, right? So inside NV, we have at most T minus 1 plus T minus 1 forbidden vertices. Right? So these are for vertices of T prime itself. Obviously, some of them can be in the neighborhood. And this is for their neighbors. And obviously, since my neighborhood is of size 2T, I have a vertex and I can embed it and I get an induced copy of T. Okay? So this is just a simple illustration why having C4-free can be useful. So let me give you a somewhat more substantial theorem by Daniela Kuhn and Derek Ostus. So they have the following result. So if G is C4-free, and H is some fixed graph, you pick your favorite graph H. If a minimal degree of G is bigger than some constant which depends on H, right, some constant, then G contains induced subdivision of H. And so let me remind you, I don't know what people know, so subdivision means, right, so if this is, say, your graph H, so what you're allowed to, so this is H, so the subdivision you're allowed to take exactly the same for vertices, but instead of H, you allow to put vertex, instead of edges of H, you're allowed to put vertex disjoint paths. So this is subdivision. Is it visible on the? So if colors are, I can use different colors. Okay. So this is a result. So again, C4-free, large constant degree immediately implies a subdivision. So why this is an interesting thing? So one class for which, very good, thank you very much. One class which I want to discuss is so-called string graphs. So what is a string? So string is just a continuous curve in the plane, right? So you take 0, 1, 2, R2, continuous. Curve. Right? And then if you have a bunch of strings, you can define a string graph. It's actually intersection graph of strings, right? So we can say this equals graph of strings, which means vertices are strings, and say edges of G, so phi of G, edges of G, so string C1 is connected to C2 if C1 intersection C2 is not connected. Right? Any two strings which share a vertex. Right? So it's very natural class of geometric graphs. You have geometric objects. These are the vertices. Any two objects which intersect give you the edges. And so if your set of vertices are strings, so you get a string graph. Now the string graphs have a very long history, right? I will not talk too much about them. The study of them goes back to 60s, and people prove very interesting result about string graphs. And one of the question is you want, which people were interested in, I give you a string graph which satisfies certain restrictions or from certain class, and you want to determine how many edges it has, right? Okay, and so here's a claim of the sort, right? Maybe before I'll give you the claim, let me make an observation. Okay. String graphs do not contain induced subdivision of one subdivision of K5. Right? So first of all, what is one subdivision of K5? So you take 5 vertices, all pairwise vertices are connected, but instead of connecting them by an edges, you say you connect them by path of lengths to right. So this is one subdivision of K5. Right? Okay, so you take this, take this, right, and you take this. So one subdivision of K5. Now, right. So what I claim is that string graph does not contain this as a induced subgraph or even subdivision of this as an induced subgraph. And this is really to see why, because we know that K5 is not planar. So imagine this would have been a curve, 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 this would have been a curve. Then this point is also a curve which should intersect these two. This point corresponds to a curve which intersects these two, and so on. And because it's induced, no other intersections are possible, right? So this follows from the fact that K5 is not planar. Right? So think about that every point is a curve, and this curve should intersect only these two curves, nothing else, because that's exactly means that this graph appear in the string graph as induced subgraph. Right? And so therefore, so for string graphs, so this particular H, right, if you think about this as being my H, this H and its subdivisions cannot appear as induced subgraph in a string graph. And therefore, as a corollary, I will get a kind of a result of the type which people cared about, that if G is C4-free string graph, so if your graph is C4-free, then because of the result of Kuhn and Ostus, right, the number of edges in G is right, n is the number of vertices in this top. Okay. The number of edges is this, or in other words, maybe let's put it, is at most C times n for some fixed C, right? So it's really bounded by some constant epsilon, right? Exactly because it's C4-free, and if its degree would have been, it would contain an arbitrary subdivision of arbitrary graph H, but I gave you a specific graph H, which does not appear. Okay. So this is a motivation, maybe some bunch of examples, which shows that if you know that your graph is C4-free, it helps you, right? So certain bounds become small, certain results are easier to prove. Now this is another thing which we know very well, or if you never heard, I will tell you in a few words. Another class, another situation which is very convenient when you work in extremal combinatorics are dense graphs. So the graphs which have, say, n vertices and quadratically many edges. So why those graphs are sometimes easier to deal with? Because we have this powerful tool called regularity lemma. So if your graph has quadratically many edges, the regularity lemma essentially tells you that you can partition this graph into finitely many blocks, such that edges between these blocks behave like an edges of random graph of corresponding density. So you see what the density between blocks are, and the edges which you get after the partition behave like a random graph of that density, and because of that, there are, again, it's a quite powerful tool, you can prove many results on the set. So now you have two things, right? You have one class of graph which are C4-free graphs, which are sometimes convenient to deal with, and the other graphs are the dense graphs. And the lemma, the key lemma which I'm trying to present and kind of popularize for you, and hopefully you will find also some application of this lemma, in this dichotomy lemma, which says that you essentially, from various equations, and I will give you an example of such equation, you can always reduce to one of these two scenarios, which are very convenient, right? And so what I mean by this, so here's a lemma, so maybe we call it theorem, because it's, right, it's not something short that I will show you in the proof. It's about 6 pages of arguments, so it's kind of a big involved lemma. So for every k, there is C of k, constant which will depend on k, such that the following holds, such that the following holds. Right? So let's make sentences short. If G is a graph with meaning, say, average, with average degree, P, then I have two scenarios. Then either, the first thing, G contains an induced C4-free subgraph with minimal degree, maybe C4-free subgraph G prime with minimal degree, delta of G prime is at least k. Right? So you always can think about k as a large constant, which you will have in mind for some application with which you start. This will give you another constant c, which I will later explain what this thing is. Now somebody comes, it's really adversary comes and gives you graph G with average degree D. D can be arbitrary parameter, it doesn't relate to this K. And then you can find two scenarios. Either inside G, you can find an induced subgraph of G prime, such that G prime is C4-free and has large minimal degree, this K, which we want. Or G has a subgraph, say, with subgraph G prime, with G prime having d-vertices, and E of G prime is at least the C times D squared edges. Right? Which means this G prime has constant density, has quadratically many edges, and actually this is your original D, right? So you're not losing anything. Obviously you're losing because this constant C, right? The number of edges is proportional to D squared, but this constant C obviously will go down the larger the K you choose. But if your K is constant, which you know from your application in mind, then this C would be constant. D typically in application you have a very huge average degree to start with, so you preserve. Is this clear? Right, so this is a lemma, so if you need to take anything from this talk, is this lemma, because that might be useful. So again, you have your favorite problem in mind, you have your graph, which has average degree D. D can be very big, better to be big, right, but it, whatever you have. And then by applying this lemma, you can find one of two scenarios. Either inside G, you can find a C4-free subgraph, which is an induced subgraph of your graph G, and it has large constant minimum degree, or you can find a really dense subgraph, like the d vertices with quadratically many edges. Very good. So what I want to do in the rest of the talk is to persuade you, to show you a couple of applications, to persuade you that this is useful. This can be useful, at least for a bunch of applications which we have in mind. So, right, maybe to avoid your criticism, I'll do self-criticism. So all my application would be of certain kind, right? And indeed, we so far didn't yet have other applications. There are many, but they're all rather similar, and I'll tell you to what. But again, the feeling is that it should be useful for other stuff as well. So the type of questions which I will discuss is so-called Zarankiewicz-type problem, right? And so let me remind you what is Zarankiewicz-type problem is. So it's a question in extremal graph theory, which asks the following. Suppose if G is n-vertex graph without complete, say, bipartite graph with parts of size, so maybe even ST, let's put me ST, where K, ST is S vertices here, T vertices here, and all edges. Right, so you give me a graph which does not contain a given bipartite subgraph complete, because obviously this guy contains every other bipartite graph. As a subgraph, without KST as a subgraph, not induced subgraph, just subgraph. How many edges G can have? Right? So this is one of the very classical questions in extremal problem, and this question was posed by Zarankiewicz. That's why we call it Zarankiewicz problem. And we know this is a famous theorem of Kovary, Shosh, and Turan, I think from 54. Then the number, right, KST3 G has your G is at most some constant which depends on S and T, n times 2 to the 1 minus S edges. And there is a big open problem whether this is tight, and we know that this is tight in some cases, for example, if T is much larger than S, or for S being, say, 2 or 3, but in general we don't know that this is tight. But that's a kind of just an umbrella, as a name. What is Zarankiewicz problem? Now, what people really study nowadays, in addition to this problem in many areas of combinatorics, is what I call Zarankiewicz-type problem. So let me tell you what it is. So these problems appear in geometry, in structural graph theory. So in this type of problem, you have F is a class of graphs. You don't look on all graphs. So here we look on all graphs G, right? We put no restriction. But now you have some class of graphs which is hereditary closed. which means it's closed under taking induced subgraphs. So for example, class of planar graphs, I don't know, class of various like intersection graph of strings or polytopes or things like that. Right? So if you take some bunch of polytopes and you reduce it, it's still intersection graph. Right? So you have a F class of graphs which is hereditary closed, and suppose G from this class is KSS free or KST free, then how large is PFG? Right? So now I want the same equation as before, but I will restrict only to this graph. So, so for example, I take, in this talk you'll see lots of various geometric graphs, mostly. I'll assume they're KSS free. I want to know how many edges. There are, obviously, I always have this bound, right? Because this bound is true for all graphs. But in reality, when I have some interesting hereditary class of graph, because it's hereditary, it has some properties, I will get much better bounds. Right? I will get much stronger estimate on the number of edges. So let me give some examples of what people consider. Right, so examples. Right, that's the graph. So what F can be? So we said F is string graphs. I will explain the names. F is semi-algebraic or semi-linear. This I'll say what it is. F is graphs with bounded VC dimension. F is visibility graphs. So I'll mention some of these things in the talk. So maybe let me start by defining what is a semi-linear graph. String graphs we already defined. Visibility graph I will talk in this talk. Graphs with bounded VC dimension is a very interesting class of graphs. So what it happens there, you take the neighborhoods of the vertices in the graph. It's a collection of sets. And there is this notion which comes from learning theory, but it's a very useful notion in geometry, in algorithms, that these sets, they have bounded VC dimension, which means if you take their intersection with a given set, they cannot shatter it, which means they cannot produce on some very big set all its subsets by taking intersection. So the VC dimension means D, that if you don't have D vertices in your universe such that if you intersect all your sets with the set of size D, you produce all subsets, all 2 to the D subset. So this is the VC dimension. And if your graph has bounded VC dimension as a neighborhood, it's a very strong property. And you can write, these are all the hereditary class of graph. Any questions? So these are type of things. So I want to, in the rest of the talk, to show you that if you have a graph of this sort, and you in addition tell me that it doesn't contain a complete bipartite graph KSS, then it cannot have too many edges. And I will show you that this lemma is very useful. Any questions? So let me first to talk about semi-linear graphs. So what is a semi-linear graph? So these are geometric graphs. So imagine you have 2 sets of vertices in RD, right? So semi-linear graph is G is a on this vertex set X union bind. So these are the vertices, and then X is connected to Y is determined by, say, H, some number, fixed number, what we call complexity, of linear inequalities. So you give me inequalities in 2D variables, h different inequalities. H typically would be constant. I mean, if h grows, the graph becomes more and more complicated. So I will look on a semilinear graph of constant complexity, and then whether x is connected to y is determined by these inequalities. And actually, right, you can think about this as a Boolean function of this inequality, right? So some inequality I want to be big, some bigger or equal, some inequality I want smaller or equal. So you give me h inequalities, you tell me in the first inequality is less or equal, in the second bigger or equal, in the third is again less or equal, and so on. Then if I want to know what are the edges, you take point x, you take point y, and you put inside. If the inequality satisfies exactly the way you want, you put an edge, and otherwise you don't. Is this clear? So let me give you an example. It actually would be, let's keep this lemma, because I need it. This would be exactly an example of such graph. So here's an example which I want to discuss first. Example is A is a set of n vertical segments B is a set of n horizontal segments, right? And then if my vertical segment intersect horizontal segment, so it's say this is my vertex V vertical, this is H, then V is connected to H, right? If they share vertex. And observe that this can be verified by writing inequalities, right? Because this vertical segment is determined by two vertices which have coordinates, and then you know, right, that this coordinate, what is it, x should be between coordinate x of these 2 points, coordinate y should be between coordinates, coordinate y of this between coordinates y of these 2 points, and then there is an intersection, and otherwise it doesn't. So I can write four inequalities on the numbers which are involved endpoints of these segments to determine whether they intersect.
So you have somehow two parameters here, like the space where you represent your vertices, this is D, and then you have H.
Exactly. And typically, right, the H is really important. I want H to be small, right? This is a complexity, and D I also will want to be small, right? So basically, these two things are fixed, but the number of points can be huge. And if any of these things you start increasing, you get a more complex graph, and at some point, there would be lots of hidden constants which would depend on this D and H, and I will tell you occasionally how they depend. But obviously, if this thing can go crazy, then almost anything you can represent in such a graph. Actually, it's a good point, maybe, two remarks before we proceed. So first of all, observe that one interesting way how to describe this semi-algebraic graph, and maybe it's more appealing. So basically, any semi-algebraic graph of complexity H can be obtained as follows. You have a bunch of points on one side and bunch of polytopes in d dimension on the other side, where the hyperplanes which define you this polytope, so if you're in 2 dimensions, this would be polygons, have at most H different slopes, because this H inequalities. And then your graph is exactly incidence graph, whether this point belongs to this polytope. Right? This is the most appealing way to describe the semi-linear graph. Now, when I mention semi-algebraic graphs, so semi-algebraic graphs are extension of semi-linear graph, where instead of linear inequalities, I can write polynomial inequalities. But then again, there is a degree of this polynomial, and again, I want it to be bounded, fixed, because if I can do the crazy things, then I get two general graphs, and people really good. But this is like a very good example, okay? Okay, so this is my graph, and so the theorem which I want to prove. So here's the theorem, which was proved by us. So Hunter, Zarankiewicz-type, come on. but this extends a certain work by previous authors. We kind of improve their bound and get absolutely tight result. It's Chan, Keller, and Svorodinsky. It's kind of their problem, and it's exactly the result which I promise you. So if G is a graph incidence, let's call it intersection graph of segments as above, right? With no KSS, then G has at most big O of S times N edges, right? And so it's absolutely tight. So observe that we understand the number of the edges of this graph very well. We will know how it will depend on the parameter S, or this complete bipartite graph. Forbidden, of course, there is bigger notation, but that's really absolute constant. I don't know, 1,000. Right? So if you give me vertical and horizontal segments, and you tell me that this graph doesn't contain a complete bipartite graph of size S, then it has at most S times N edges, and observe that S does not need to be constant. So actually now, because I wrote you everything explicitly, you can take your S to be, I don't know, N to the 2/3, and it still would be valid, right? Okay. So any questions? Very good. So let me prove this. Prove this result, and so I want to actually illustrate this lemma. So remember, the lemma says that I start with arbitrary graph, and I either find inside an induced C4-free subgraph with minimum degree k, or a dense subgraph. And so I'll do this exactly here. Either G has an induced C4-free subgraph G prime with K, and observe that here immediately, and this typically for this application, because of other things, I immediately reach the contradiction. Why? Because this is a string graph.
So
And
you
because
know that you have lots of edges, right? Or what? You go by contradiction?
no, right? So if I'll get contradiction by choosing this K large. So by choosing K large but constant, right? And this is immediately, of course, implies that I have a lot of edges. But again, there is this constant which I got from this result of Kuhn-Nostus, right? There is this large constant which will guarantee me that C4-free graph with that many edges, with that minimal degree, contains subdivision of fixed graph H. And this fixed graph H was this one subdivision of K5, and which I know does not appear in string graph. By choosing K large and noticing that G is a string graph, right? The large minimal degree implies induced subdivision of one subdivision of K5, and this is two things give me contradiction. So this cannot happen, right? So because this is a very special case of string graph, I would not, the only thing it says I would not be able, I can choose this K large enough that I would not be able to find inside an induced C4-free subgraph with minimal degree. So therefore, let me get here. So therefore, I'm in the second case, right? So hence, G has G prime on d vertices. D was average degree of G with C d square edges. Right, where C is some constant which depends on the scheme, but these are all constants. And I obviously assume my D is large. Okay? So now I have this dense piece. Now I do one more step, which I will just tell you that it's true. I will not explain you, because G has G prime, which is subset of G, because they're all string graphs, has bounded VC dimension. Most of the geometric graphs, they have bounded VC dimension. You can easily see that this thing cannot, if you take sufficiently many intervals and you start looking on the intersection bundle, you cannot realize all to the D patterns on D intervals. So these graphs have bounded VC dimension. What happens with bounded VC dimension, if you have a dense subgraph inside, you can amplify the density to be as close to 1 as you want, right? So we can assume, let me be precise, not the whole graph, but we can assume to find a bipartite graph. Maybe let me write. We can assume to find inside a large proportional to D cross D bipartite subgraph with density 1 minus epsilon. Okay, so that's a typical situation. So if you have a graph with bounded VC dimension, whose neighborhoods have bounded VC dimension, with quadratically many edges, you can, there is the same regularity lemma which I mentioned. There is a very strong regularity lemma for graphs with bounded VC dimension, which means if you apply these bipartite graphs which you find which are nearly random, in addition they have basically density either 0 or 1 minus epsilon. And I take one of those, and because I have quadratically many edges, I will have such a graph. So let's assume we now have this situation. So what it means? It means we have roughly D vertical intervals, called segments, roughly D horizontal. Of course, there's some constant here, but I will not write it horizontal. And 1 minus epsilon fraction of pairs intersecting. Okay. And now I claim that inside, so observe, right? So this thing has density 1 minus epsilon, bipartite graph, right? Vertical versus, and I claim that I can find inside a linear subgraph which is complete. Now, if your graph would have been random, of course, this would not happen. We know that if you take a random graph, n by n, bipartite graph, and you put edges with probability 0.9, still the largest complete bipartite subgraph would be logarithmic. But these objects are geometric, and we can capitalize on that. So let me show you that if you have these vertical segments and horizontal segments and 1 minus epsilon, say 1 minus epsilon would be 0.9. I don't need this epsilon to be minuscule. Intersect, then I get a maybe by deleting vertices of low degree, let me make a simplifying assumption, I mean, which is absolutely standard. Every time if you have a segment which intersects few other segments, throw it away, it's only increase the density. By simplifying the assumption, I will assume that every segment intersects 0.9 fraction of other segments. Right? So I'm not only doing density, but I clean it to have large minimal degrees as well. Is this clear? Right. So this is just absolutely standard. And so now I'm ready to do the proof. So you have your vertical segments, you have your horizontal segments. Every segment intersects 0.9 segments of other kind. So you do the following. You start with vertical segments, and you find me two segments, which I draw you in red, which I called left and right. And you can easily understand why I call them left and right, because I have vertical segments. So I look on these segments and I pick the first one, like according to the coordinate x, I call this left. This is the leftmost one. And I pick the rightmost one according to the coordinate x, and I call it right. So all other segments, horizontal segments, they live here, right? Right, so this is leftmost, rightmost. Now observe that the common neighborhood of left and right is at least 0.8 of all horizontal segments. So you agree that because this guy intersects 90% of horizontal segments and this guy intersects 90% of horizontal segments, the horizontal segments which intersect them both is at least 80%, so majority, okay? So I have a lot of horizontal segments which intersect this left and right, so let me do them in green. So I look on all these 0.8 fraction, and I choose two of them, and with very simple names, top and bottom, T and B. Obviously, I take the highest horizontal segment that they both intersect, and the lowest horizontal segment which they intersect. And observe that there are many other horizontal segments which they intersect, which all live here. Right? But now you see, you get a complete bipartite graph of intersection, because all these vertical ones, all ones, right? Because I said they were between these two red segments, right? So all verticals were between these two. So then there was a lot of green ones which they jointly intersect. I took top and bottom. So all these green ones, they lived here. So this gives me like, right? So this implies that all vertical ones intersect, all verticals ones intersect this common horizontal ones. Which gives KSS, where your S is proportional to D, right? Right. Say proportional to number of segments, which is proportional to D. Is this clear?
I don't see it, so
let's.
so I took the extremal.
So I reduce my problem to the collection of vertical and horizontal segments.
Yes.
The number of segments, vertical and horizontal, is proportional to D, maybe D divided by million. I lose only constant. And moreover, I know that this bipartite graph has density 90%. And once it has density 90%, I can clean it. I can delete vertices which have low degree to have really minimum degree 90%.
And then you take extremal left, extremal
So
right.
then I look on vertical segments, and I took the leftmost and the rightmost. So observe, right, that I see where we're going and I see what I didn't say. Very good. Good to have audience which listen. So observe that, very good, I will correct it. So observe that between this, so all the segments, other vertical segments, they live between these two, right? Then these two vertical segments, L and R, have 80% of horizontal segments in their common neighborhood, right? So these guys live here, right? Now I want to say, so I'm sorry, I didn't say correct. Now I take the top of most of them and the bottom most of them, T and B, which intersect these red ones, right? Very good. And so now, so this is not correct how I wrote it. Let me correct it. Yes, very good. So now what I'll do, so I will take for this T and B all red segments which intersect both of them, right? So note that the common neighborhood of T and B is also 0.8 of all vertical segments. So which means that there is a lot of these red guys, which were between this and here, which look like that. And there was lots of green guys, which was in common neighborhood of these two, so they were like that. And now you would agree that these green ones and these red ones all pairwise intersect. And this is my complete bipartite graph. You're absolutely right. I forgot one important point. Right? So is it clear? So I start with left and right. I take their common neighborhoods, these green segments. Then I took top and bottom, and again take their common neighborhoods. These are vertical segments. And now what I have every vertical segment lives here, and it should intersect top and bottom because it was in their common neighborhood. Every green segment that it lives between T and B, and should intersect these two red guys because it was in their common neighborhoods. And then obviously every green and every red should intersect. And so then we will have every red segment intersects every green segment. And this gives me KSS with S proportional to D. Okay, so this is now, right, so very good, I forgot to mention this. So this is, I think this is a main proof I will show you in this talk. I will not show you other proofs, but this is an illustration how this lemma works, right? So we started with the lemma. We first went to C4-free case. We know to say that this doesn't happen because of we don't have subdivision, induced subdivision of something, and we know that C4-free graph with large minimal degree has induced subdivision of everything. And then we go to the dense case, and dense case, because of the geometry, or I said in some other cases because of regularity lemma, you can handle because it's a dense case. Any questions? Very good. So maybe let me continue.
So
yes.
How are you using actually the fact that these are horizontal and vertical segments? Like, how far can you generalize this argument?
Very good. So here is a more general. So let me keep this dichotomy lemma still up. So here is the most general result in that direction, which we prove.
Because on one side of the dichotomy, you just need string graph.
Yes.
Or actually excluded induced subdivision. Or
right.
Something.
So here is the most general question in that direction. So as I said, this is a question of Basit, Chernikov, Stanchenko, Tao, Star, and Tao. And so what they ask is that, right, so G is exactly the semi-linear graph. of complexity, of constant complexity. So you remember, so this is a graph, this is, say, incidence graph of points and polytopes, and these polytopes with constant number of slopes. Right, so the hyperplanes which define them have constant number of slopes. And then suppose G is KSS-free. What is the number of edges? So this is kind of a, say, most general question in this direction. But I will give you some more examples, but that would be kind of a question in this direction, right? And they have some results of this sort in their paper. They not only ask this question, but they prove some results. They ask how many edges you will have, and the answer is not linear for this problem, but almost linear. So they proved that E of G is at most some constant which depends on H and S. You remember H is a complexity. H is a complexity. Number of slopes. Number of slopes. Let's think even in 2 dimensions. Think you have polygons which defined by at most H different lines. N times log n to the power H. So this H appears here. So that's what they proved, and they asked what is the correct answer. And so we can completely solve this problem, and I'll tell you what the answer is. I will not explain you, right? So we're in D dimension, right? In RD. So all this happening in RD. So apparently, so in RD the answer is some constant, which depends now only on H, because all other parameters I will make explicit. So S times N times log N divided by log N to the power D minus 1. Right? So really know what the answer here is. Right? So if you take, say in plane, right, you take points and polygons, and these polygons are determined by H slopes, and you ask, look on this incidence graph, and suppose your graph does not contain a complete bipartite graph with sides of size S, so S points, S polygons, which completely intersect with each other, then the number of edges is at most N, right, the number of polygons and points, times your S. You can make S grow with N because it's all very explicit, times log N divided by log N. In the case of planes, would be to the power 1, and generally d minus 1, and all these dependencies, obviously except for dependence on H, which is a complexity of the thing which we always assume constant, we know precisely this.
So you have also a lower bound?
We have a lower bound construction, yes. Yeah. Actually, it's not our lower bound. It's more or less a lower bound, which was, I think, Eisen, Basit, Chernikov, Stanchenko, and Tao. There was a follow-up paper by Dima Zakharov and Ishtan Tumon. So we just, our proof gives whatever constructions they had in this paper. So we bounce with that.
So with logs, yeah, to the power. So
Right, with logs to the power, yeah.
How about segment graphs in the plane? So intersection graphs of segments, but not horizontal vertical, but just general position segments.
So intersection graphs of segments in the plane. So if you give me intersection graph of segments in the plane, so they have this theorem, so it's a bit different. So we need, right? So they always have or complete or empty bipartite graphs of linear sites. So this is not related to this, it's some topological statement. And so we can try to use it. So about them, this Zarankiewicz-type things, one is not.
Okay. So there will be the same linear value for them. So how about general string graphs then?
So for general string graphs, so there are also these results known. I don't remember on the top of my head because right, we have some results in the paper, right? So for them we also, I think, know various estimates, right? But it's not. We have something in the paper, but it's not that clear.
But because looking at your argument here, like the first part works because it's
right.
just about those induced subdivisions.
And the second part is more complicated, right? Because you need to.
The second part is you need some topological argument, but there is also this VC dimension statement.
But VC dimension almost always true for geometric graphs. So the only thing I'm using about VC dimensions, the geometric graph have bounded VC dimensions that typically is a correct statement. Right, for at least maybe like for various geometric graphs, just because of geometry, hyperplanes, boxes, and so on. So that's not good. So once you dense, you can always assume that your density almost found, but then you still need to do something. Okay. So let me. Okay, so this is right, and again, there are more results. I admit that I don't remember all of them by heart. We have in the paper because the paper is about 40 pages. So we have a lot of application of these things, but maybe I want to mention some which are kind of more visual ones. Okay, so let me now talk about this visibility graph. So what is visibility graphs? It's again some graphs which people were interested in. So visibility graph. So you have some closed curve, non-intersecting, say Jordan curve in there. Right, so this is your curve. And imagine you put some points on this curve. This is a point, so this is K is a curve. Right, X set of points. These are vertices. This would be vertices of our graph G. And the visibility, it's exactly what you think. So any two points which see each other, if it draws a direct line between them, this line does not intersect my curve, are connected by nature, and otherwise not. So in this particular case, I will have these two connected, these two connected, these two connected, these two connected, these two connected. So maybe I don't want these two connected, maybe let me draw the curve so that this other two would be also not connected. Maybe. Top edge should be connected, yes. Yes. So this would be a visibility graph.
You connect only through the inside of it.
Through inside, right? So yes, exactly. Let's write it, x1 connected to x2, if segment x1, x2 completely contained inside. Right? And it's clear what inside means. Right? So this is visibility. Okay. So the question which I want to discuss is a conjecture which was posed for this graph by Du and Rose McCarthy. And so what they observed is that these graphs were chi-bounded, so they studied them, and in particular, because of that, they conjectured the following. So if G is visibility graph, KSS free, then the number of edges in G is at most KSS free, and vertices, let's say vertices, is linear in the number of vertices with some constant which depends on that. So that's the conjecture. That's the conjecture. So this, again, this interesting hereditary class of graph where we can get linear bound for Zarankiewicz problem. Okay, and I want to mention two specific, this is a still very open conjecture, very interesting. I want to mention two specific cases. So one case which we understand, K is X monotone. So special cases will reflect the special structure of the curve. So X monotone means that if you take your curve, then the curve has the property that any vertical line intersects it in 2 points, at most 2 points. So this is X monotone, right? And another thing, K is star shape. And star shape, say, this is star shape. Right, maybe that there is a point inside your curve such that if you draw any line from this point, it's intersect your curve only in one point. So this is star shape. So you have a center, and any line from the center will intersect your shape in one point. So these are two cases which we understand. Right, so I need to this. So this conjecture was proved for these two cases, not by us. So the people who solved this conjecture was Ackermann and Hesse, I hope I pronounced correctly. But again, what we can do with our lemma is get a precise absolutely tight bound. So the theorem which we have, right? So for if K is X monotone or star shape, then and the number of edges exactly in this case, KSS free is at most, right, again, very accurate estimate. So this is absolute constant. So you really know the correct dependence on S. And again, you do the C4-free case. It's again not very difficult to see that would not be materialized. And for dense case, we need some bound. So we reduce it to some arguments on ordered graphs. So you kind of need a bounded case-free ordered graph with no particular fixed ordered magic. So that's how we get the upper bound. Okay, so this is another example. Okay, and maybe let me finish with one more example just to show you that it's not only works for geometric graphs, so it's some other question, some other class of graph which was proposed by Jacob Fox, Ray Kondenadov, and Hui Pham. And so they wanted a class of graph which somehow generalize both random graphs and both graph without complete subgraphs. And so here what they come up with, they said G is alpha, maybe let's see T, sparse if for every x, y in Vg subset of size T that is joined, the number of edges between x and y is at most 1 minus alpha T squared. So basically, it's a bit stronger. So not that you don't contain complete bipartite graph of size T, but you have slightly less density, right? So this is alpha T sparse graphs, and they study a lot of properties of alpha T sparse graphs. So in particular, they proved theorem. Right, if G is alpha T sparse, and has no induced 3 T of T vertices, then G has at most P times n edges. So this T does not induce 3T, just the constant will depend on T. Right? So again, so remember we started by talking that on this Garfash chi-boundedness conjecture, so it's a little bit motivated by that. So you give me a graph which doesn't have induced 3T, if in addition your graph is alpha T sparse, not only that it's chi-bounded, it has bounded degree, right? So they even get. And so they conjecture same holds if instead of forbidding induced 3, we forbid induced subdivision of some graph H. So obviously, right, this is a right. So you can think about my two examples in the beginning, right? So when I was saying that you take C4-free graph, you can, if you forbid me induced 3, I know how to bound the number of edges. Then I told you there is a more difficult theorem. It's indeed more difficult theorem. It takes a paper to prove that if you are C4-free and you don't have induced subdivision of some fixed graph, you have linearly many edges. And so they ask, so can you get the same thing here? So suppose you have alpha T sparse graph. You give me your favorite graph H. You forbid me to have an induced subdivision of H. Does your graph has linearly many edges? And actually, does your graph even has this linear dependent both on T and N?
So this is for every H? Or for
this is for every fixed H. H should be fixed, right? So for some H fixed.
So not necessarily a tree, right?
Not necessarily a tree, yeah, no. So that's an extension, right?
And you mentioned this theorem because they also use this level, or?
So, no. So they ask this, they prove it for tree and they ask this question, and the theorem which we can prove, right, that in this case, indeed, right, E of G is at most big of, so constant will depend on H, T times N. Right? We indeed can prove it, and we indeed can prove it using this lemma. And again, what already like a similar thing which Bartosz said. So you start with the first case, which kind of will trivially follow from Kuhn and Ostus, because if I can get in my graph an induced C4-free graph with many edges, then I have subdivision of everything which I want. So this case doesn't happen. Then I get a dense graph, right, on d-vertices, which is almost what I want. But then there is some trick to go from density constant to density near 1. And if I get density near 1, then obviously I will violate that alpha t sparse no matter what alpha you gave. And that's somehow right. But that's just I wanted to show you because it's a slightly different, because all our application was geometric, but this is a little bit more graph theory. So this is all what I wanted to tell you today. Again, it's very good I managed this time not to delete this lemma, and this is a lemma which I again want you to remember. That's maybe you find application of this lemma in the work you have. You start with arbitrary graph with average degree d, and then you have a dichotomy. You either can pass to induced C4-free graph with large but constant degree, and probably because of your problem, maybe you can rule this case out, or you can find then very dense graph, the graph whose number of vertices your original average degree with quadratically many edges, and maybe regularity lemma or something else again gives you what you want. And if you know any new application of this lemma, I would be very interested.